So let's look at the direct comparison test. The hypothesis is this. So suppose all terms an and bn are non-negative, so no negative numbers allowed. I could say two things. If the sum of the larger terms converges, so if bn converges, then so does the sum of the smaller terms. So if you have a positive sequence, positive terms in your series and they converge, and you make those terms smaller, well then the smaller terms converge as well. And then number two, if the smaller terms diverge, then so does the larger terms. So intuitively, I hope it makes sense. If you add up these numbers and they get arbitrarily large, and you make the numbers bigger, the bigger sum also gets large. So let's do some examples. All of these questions are to decide whether or not the sum converges or not. So let's look at the sum of 1 over n to the n power. I'm going to make the terms bigger. So this is less than or equal to the sum going from 2 to infinity of 1 over n squared. N to the n is bigger than n squared. So 1 over n to the n is smaller than 1 over n squared. Now I know this converges. This is a convergent p-series. With p equals 2. 2 is larger than 1, so I have a convergent series. That means my smaller series also converges. Convergent. Another example. What about the sum going from 2 on of 1 over log n? Well, that's bigger than or equal to the sum going from 2 to infinity of 1 over n. Log n is smaller than n. So 1 over log n is bigger than 1 over n. Now this we know is a divergent harmonic series. It's also a p-series with p equals 1. But this is an example we've seen a few times, diverges. So this sum diverges as well. Let's do another example or two. How about the sum going from 0 to infinity of the absolute value of sine n over 2 to the n? So sine n is always in between -1 and 1. So the biggest that the absolute value of sine n could ever be is 1. So this is smaller than or equal to the sum of 1 over 2 to the n. I just took the sine n, replaced it with 1. Sine n is always less than or equal to 1, so I get this inequality. And this, we've seen, is a convergent geometric series. In fact, we know what that adds up to, but nevertheless, it's a convergent series. So my smaller series, convergent as well. How about one final example of the direct comparison test? Let's do the sum going from 1 to infinity of n cubed plus n plus 1 over n cubed times the square root of n. Okay, this is bigger than or equal to the sum going from 1 to infinity. Now I'm just going to drop the n plus 1 terms. I'm just going to omit them. I'm not going to add in n plus 1. I got to get smaller, so I'm erasing some positive terms here in the numerator. Got to get smaller. So this is bigger than or equal to n cubed over n cubed root n. That's equal to the sum going from 1 on. This is really, if you want to write it this way, 1 over n to the 1/2 power. This is a divergent p-series with p equals 1/2 and 1/2 less than 1, less than or equal to 1, so it diverges. Okay, so that's an example of the direct comparison test. It's kind of an easy test to use once you know what you want to compare with what. So I kind of hit a little bit of the tricky part in doing these problems. I kind of knew what I wanted to compare. There's no hard and fast rule on how you want to decide what to compare with what. You kind of got to get a feel for it, get practice. So get some practice with these in the homework. All right, I'll see you next time.